The following content has been provided by RWTH Aachen University.
Good morning, everybody. Let's get started with DIS1 today. So we will start with a very quick review of what we talked about last time, and then we will dive into a continuation of psychological basics of HCI. So we'll cover things like Gestalt laws, the information content and user interfaces, and questions like visibility, and a super important concept of affordances and signifiers, which will also start getting us into this book by Don Norman that you'll be reading the next couple of weeks. So first, and this will immediately ask you guys to speak up and participate. Got a couple of questions. We took a look at HCI as a domain, as a research domain and a practitioner's domain, and we had 4 big areas in this overview diagram. Maybe you can raise your tiny little blue hand if you can tell us what those 4 areas are. Elena, go ahead.
I don't think that I can quote all 4, but I think there are human, computer, then the context or something in the direction, or like culture.
Yeah, so very good. Human, obviously, and computer, those are sort of the given ones. And then we've got the context of use, sort of the social environment in which the interaction happens. That's its all sort of research field. CSCW, computer supported collaborative work, looks at that. And then there was a 4th area down below that we will actually spend quite a bit of time in DIS1 this semester. Anybody remember which one that was? Aparna, go ahead.
User interface.
Well, the user interface is kind of in between the human and the computer, and yes, it has a couple topics that are specific for it, like ergonomics or input-output devices. But there was a 4th area in the bottom of that diagram that actually, if you think about the things that we'll cover in part 2 and 3 of this class this semester, those are from that area. Well, we're now talking about the human. We won't be talking about the computer side much in this class. So what's left? Yeah, Lucas.
The design and the development process.
Yep, that's right. So the whole process of how do you get to a good user interface design, because the rules I'm going to give you today, and you know, those kind of like, you know, they always apply to human psychology, right? They're not variable. They're constants that you can always work with as an interface designer. But for a concrete application area, you really need to figure out what is the exact task, who are these users, what's their profile, what's the context of use. And in order to determine the answers to those questions, we have a set of tools and processes to do that. Right on. So then, oh, and example systems are also from that bottom area there, and we'll look at a couple of seminal HCI systems over the years that, you know, kind of like an architecture class. Right, then we talked about the CMN model. So that consisted of a couple components. See if you can rack your brain and recall some of those without peeking at your notes. Parts from the, yeah, Aparna, go ahead.
Perceptual, cognition, and the motor, 3 different parts of the human brain or the processes that are present.
Right, and that's an important distinction. This is the processors, right? The perceptual processor, very good, and then the that takes in you know, visual auditory input in that simple model. It doesn't model haptic input, for example. Then we've got the cognitive processor that deals with memory, storage, and retrieval, and you know, in decoding rules and deciding what to do based on what stimulus that's coming in. And then we got the motor processor that actually triggers those things. Remember, this is an engineering model. We don't actually have 3 processes in our brain, obviously, but the point of the model is just to arrive at useful numbers that give us good estimates of how people will perform under a certain situation, so that we can build interfaces that support them ideally. There was another part of that model that's sometimes forgotten. We have processors, but we also have, what's the other part of the CMN model? It's almost like with a computer, really. Yeah, Marius, go ahead.
We also have memory.
Exactly, right? And again, we've got different kinds of memory, short-term memory, visual auditory image store, long-term memory, and so on. Good. And this is a little trickier. You may not recall these off the top of your head yet, but just to make sure that you have an intuition about this. If you go through a full loop of I see something, like a light goes on, I need to react to it, to press a button, my finger's already at that button, basically hovering over it. So no Fitts law, shenanigans, we're just pressing that button. How long does that roughly take me? From the moment the light gets turned on to the moment the button is pressed? How long will that take? On average, obviously, people are different, and over the course of a day or a week, people will differ in performance. But what's the average that the model gives us? Fabian?
Yeah, can you hear me?
Yep.
It will take around 270 milliseconds, I think, because the perception takes 100 milliseconds and the other two take 70 milliseconds.
Right, and that adds up to 240 milliseconds, but you're right. Yes, exactly.
Yeah, right.
Which means, and in another word, that's a quarter of a second, right? So that's the reaction time, you could call that, between you seeing a stimulus, if you're ready to react, right? Not when you're surprised because somebody runs in front of your car, but when you're ready to react, you're looking at a screen, waiting for the light to go on, and when the light goes on, you press a button. That takes about a quarter of a second. And yep, so those are the key numbers from these three processors. And if we need to make more complex decisions, like react to something because we saw a letter and we're supposed to decide whether it was an uppercase or lowercase letter, then that will require actually 2 cycles of the cognitive processor, and that will lead to longer times, right? That adds actually roughly another 70 milliseconds to the bill if you need to make a decision before you react. So let's say a light goes on, and if it's green, you're supposed to press the button. If it's red, you're not supposed to press the button. That takes another step of the cognitive process to decode that and make that decision, and it'll take a little longer than a quarter of a second. Roughly 1 more cycle in the cognitive processor. Definitely take a look at the CMN book and the paper if you want to find out more about this. It's really interesting work to see how they arrived at this and how closely this actually maps what you find in cognitive psychology experiments, right? Okay, and then Fitts law. So what does Fitts law describe? Like what is the idea behind Fitts law? What does it tell me? Can anybody give me a rough first shot at a definition of that? Yeah. Bilit, go ahead.
It basically says it's faster to hit larger targets which are closer than the smaller targets which are further than us.
Exactly. So that's the general qualitative message of Fitts law. And the one thing that you guys should keep in mind for now is that this is not a linear relationship as you might expect. So something that's twice as far away will not double the interaction time, but it's actually a logarithmic relationship, right? So if you have that, if you keep that in mind, then that's a good start. Ultimately, you'll have to learn the exact formula for this, at least for your assignments and the final. But that's the qualitative message behind it. Okay, so today we're going to continue that, and first we're going to talk about Gestalt laws. Gestalt laws are basically telling us how people make sense of their surroundings. And this is, again, with some significant participation of the audience. So first question here, does anybody recognize something in this collection of splodges? If you can see something, please press yes. And if you don't see something, please press no. And we promise we won't be recording the results here, so you can be honest, it's fine. So yes, you can see something. No, if you don't see something. If you click neither yes or no, to me that means you're still asleep. All right, good. We got a couple people that are saying, yeah, I'm not really seeing anything. Of those that are seeing something, Mostafa.
So I think I see a dog drinking, or like from a lake.
And there's a tree over there, like on the corner.
Good. Okay, so we're seeing a dog here. I've got this sketched in for those that aren't seeing it. That's the dog with its nose down on the ground, doing something there, maybe drinking. We don't know. Maybe it's a patio. Maybe it's water. We don't quite know. And yes, and there seems to be a tree to the left there with a stem next to it. All right, good. The point here is our brains are amazing, right? You can take down your hands and remove your yes and no things. Our brains are really wired to make sense of what we perceive, right? They are really tuned into this. Here's the second question though. Can you now, if I remove this again, can you unsee the dog? Can you look at this and just see dots again? It's really hard, right? Once we have latched onto a pattern here, we really think our brain keeps coming back to that pattern. We got a couple more of those. Just real quick here, give us a yes or no if you're seeing anything. Yep, that's a horse and rider, right, on there. If you're not seeing that, talk to your colleagues later, chat with them and ask them where on earth is that horse. There's a rider, he has a horse head and a tail and 4 legs down here at the bottom. Another one, now everybody's seeing something here, but you might be seeing, you know, a vase or some kind of, you know, container here. Or you might be seeing 2 faces looking at each other, right? Depending on how you see it. And you can actually kind of, you know, switch over from one to the other, but it takes some cognitive effort to do that. This is a famous one in which you may be seeing an old woman where the nose is right about here and the mouth is here and it's very thin. Or you might, and she's got a feather and a scarf, a headscarf. Or you might be seeing a young woman looking away with her eye here and her nose over here. And this is sort of her chin that you're looking at. And this is her ear and this is her hair. So, you know, and once you've seen one or the other, it's kind of tricky to actually switch back and forth between them unless you train yourself a bit. All right, this is both a blessing and a curse, right? We are always good at making sense of what we're seeing. Here's the final one. Here you may see some 2 dolphins swimming, and there's a dolphin here and there's a dolphin there. You may also be seeing something else, depends on yourself. But anyway, so that's the point, right? We always see things and we always interpret things and try to make sense of our world. That's how our brain is wired, and we're really, really good at this. If you have a Fabian, do you have a question or do you just have your hand up?
Yes, I wanted to add that recent internet viral events also show us that this might also happen with the sound. Like every 1 or 2 years, we get like this sound where one half of the people hear one thing and the other ones hear something different. Like the whole Laurel or Yanni thing and the whole dress thing also come to mind with this thing. I think people are so fascinated about this that there are like so many examples also from like not even intentional ones, like the ones who are drawn seem very intentional, but also
yeah, those are intentional, clearly. Yeah, right. No, absolutely, that's true. It's always a good point actually that you make to link not just to our visual sense. I'm just showing you visual examples here, but also this also works with other senses like the auditory sense. And actually, Ollie, Marcel, it might be an interesting example to include for next year to have maybe something to play back, you know, building on one of those memes. So back in the 1910s, right? So this is like over 100 years ago, a couple of psychologists got together and in the Berlin School of Thinking wrote a book called Gestalt Psychology. They established the field of Gestalt Psychology. Köhler, Kafka, and Wertheimer was their names. And their idea was they wanted to understand how do people do this? Like, what is it that makes us perceive stuff as belonging together, as a group? This is mostly primarily for the visual sense, spatially speaking, but it also actually works if you think about it in the temporal sense of, like, for example, movement over time or hearing a sound. But we'll mostly stick with the visual examples here because they're more relevant to most of your UI design questions. They found that these Gestalt laws that they discovered over 100 in total, are actually sort of, the foundation of how we bring order to the things that are around us. Not just in perceiving them and remembering them and thinking about them and learning, but also how we act and even how we move. They are extremely useful for user interface design because they tell us how we can bring order to an interface by using these Gestalt laws, applying them, and helping people to quickly and easily parse the information we're showing them. If you look around yourself right now in your room, you will see all kinds of objects, and you immediately recognize them as objects, right? If there is a gray painting in front of a white background, take a look at my background here, for example, you immediately see sort of things as belonging together simply because they are colored shapes and groups. So let's look at how that works. It's so important because when you use these Gestalt laws well, you can understand why an interface like the one that we're showing you here actually works, right? This is just pixels on the screen, but everybody immediately sees a one frame in the front here and another one hidden behind it. You don't even have to think about it. You cannot see it in any different way, actually. And so this kind of sense making is what's behind Gestalt laws. And they will really help us to understand how users will react to mostly the spatial order of objects on the screen, but also to the temporal order of things happening or sounds being played. So pay attention to these Gestalt laws, and you can actually use them to make your interface easier to use and more intuitive. And here's the first one. Now, this would normally be an in-class exercise, but this really doesn't work in the online Zoom format, so I'll have to tell you instead what happens. I usually make the last row in the classroom draw something. I show them the shape on the left here, this squiggly shape. I show it to them just briefly, and then I let them draw that shape from memory. And then I take those drawings and pass them on to the row in front of them. Again, the row in front of them only gets them shown very briefly for like a split second, and then they have to draw it from memory. I take their results and move them another row up to the front, doing this from the back to the front so people aren't peeking, right? And by the time this goes through like 8 or 10 iterations, almost invariably, we end up with a lot of these original shapes, at least like, slightly dented circles here, to end up either as perfect circles or maybe as circles with a single really prominent dent in there. So this is weird. What's going on here is that the brain is essentially running what you could call a cognitive compression algorithm. It's seeing what you see here on the left, which is a very complex shape if you wanted to precisely represent it, right? If you wanted to really store it exactly, if you wanted to give me precise drawing instructions, it's really hard. But so what your brain does is it says, wow, that's a lot of stuff. But it kind of looks like a circle, and then it has a couple dents. So I'll remember that instead. So people draw a circle and put a few dents in it. And sometimes, one dent then over the course of time gets more and more pronounced until this thing ends up being like a circle with a single blob or something. But oftentimes it just gets reduced down to a circle, because by the time people have done this 4 or 5 times, they just draw a squiggly circle. Next person sees it, says, ah, that's just a circle. And this detailed information, this high frequency information, if you want to speak information theory here, actually kind of gets lost. This is because your brain tries to store things in a readily retrievable format to spend less, if you want, less storage space to remember that drawing. And it's easier to remember to just say it's a circle with a few dents than to try to remember every single part of that line. So for user interfaces, this means that if you give something an easier shape, a straight shape, then it's also easier to remember, because people will compress your user interface in this way anyway, right? They will reduce that detailed information and will sort of, just remember the easy basic shape of it. We could call this, a cognitive compression algorithm, because people have this tendency just to remember things as clear or simple shapes, or as the Gestalt psychologists called it, the law of good shape. All right, next up, this is one with participation, and I'll just call up somebody. How about Artem Kolokoltsev? Tell me if you had to, if I wasn't able to see what's on the screen here right now at the bottom, and you had to give me instructions to draw it, roughly, what would you tell me?
So like that you have to draw 4 lines and combine 2 of them together and draw closer to each other.
Okay, so you immediately made the connection here that there's 2 groups of lines, right? So there's 4 lines in total, and they're grouped into 2. Nobody would say, well, draw a line, then draw another one next to it, or draw 2 more lines and make those really far apart, and then draw another one. Everybody sees this left pair of lines as one group and the right pair of lines as the other group. This is the law of proximity. So very simply speaking, this is kind of almost self-evident. Objects that are near to each other, we perceive as a group. And this is a very fundamental law that always applies when people look at a user interface. What that means is that when a user sees an interface, they will immediately start grouping things together simply based on their position to each other, without any other aids, right? You don't need to do anything, no boxes around stuff. It'll immediately lead to people seeing things as being connected to each other just by having this kind of law. Okay, so do we have more of those? Sorry, I have an example of this one. This is kind of like a nice contradiction of using that law. This is a picture taken from our Mensa here, which has an electronic card reader on the left, and it had this, emergency button on the right, and somebody was too lazy to actually mount that sign to the wall, so they just put it onto the fire extinguisher emergency button. Well, guess what that suggests, right? If you don't know what these 2 things are, then you will probably try to test your, Mensa card by holding it up to that, fire extinguisher box or something. So that's bad design, right? That sign, because it's so close to the emergency button here, clearly gets associated with the emergency button and not with the button on the other side there. And this, of course, is applied all the time when you see toolbars, for example, that group objects together. Then they immediately make use of this law of proximity. Next up, we got this. Again, I'll just call up somebody to tell me what they're seeing here. How about Sam? What do you think? If you had to tell me, what are you seeing? What do I need to draw? You need to unmute.
Does this work?
Yes, this works.
Okay. There are 3 rectangles right next to each other.
Absolutely. Yep. So you're immediately grouping this into 3 rectangles, even though if we take away some of those lines here, you'll see actually that these are the same lines as before. See, this is basically still showing you the the same lines with the disconnect and without the disconnect, right? So the middle lines here are the same ones as before, but now nobody is grouping those together anymore, right? Everybody is saying, no, wait, those are 3 boxes. Even though those parallel lines in the middle are very close to each other, the closure of them actually dominates, right? And this is the law of, surprise, surprise, closure. So closed lines create a shape in your mind, and thus all those closed lines become part of one thing, right? And this is, of course, essentially the whole, Gestalt theoretical foundation of the whole window metaphor that we use in GUI desktops, right? We make a box and people immediately say, okay, that's a box, right? That thing seems to be one entity. There is also a closely related law to the law of closure here, And by the way, this is new for this semester. Ollie dug into the research a little more and cleared this up for us. So we have a second law that is at work here. So when you look at these cards again, you would now say, well, okay, there's 3 cards with dots on them, right? But if I remove the cards, then you might group these dots differently, right? You're no longer going to be readily grouping them based on these cards, but you might say, oh, actually the top 3 dots maybe are on one line, the middle 4 dots are on a line, and so you might see those kinds of patterns, or you might see the symmetry between these right 4 dots here. So the cards, these rectangles around them, these closed shapes around them create regions, right? And this is also, of course, a super strong cue that we see at work in user interfaces. It's a law of common region. So anything that is inside a bounded area, so inside a closed shape, or actually inside a region that is colored with a uniform color, also appears as belonging together. This is also, of course, a basic element of the whole window metaphor that we use on desktops every day, and on mobile interfaces just as well. This should not, however, be overdone. And there is a tendency in some user interface tools and some design styles to kind of overdo this kind of, drawing boxes around everything. Here's an example where it's gotten a little out of hand. It's taken from a wonderful book called GUI Bloopers by Jeff Johnson. It's a whole book full of bad user interfaces, and you will have a lot of laughs at looking at page after page until you get to that page where you're like, oh crap, I think I did that the other day in my own user interface. So anyway, what Johnson was showing here is that this is making too intense use of boxes, right? If you look at the lower left part of this image here, you are starting to have trouble to parse, okay, which of these lines actually belongs to which of these, nested boxes here. It becomes unclear. These boxes are unnecessary, right? It gets even more extreme on the right-hand side with these like 3 lines here. That's just too much. What you could do here, of course, is just to remove those lines and instead work with the law of proximity. Just by moving things closer together that are supposed to belong together, you can create much of the same layout and grouping and not needing all those kind of boxes around boxes around boxes. Law of similarity, we got that cleaned up. It can be a good thing or a bad thing, right? So that means basically things that look the same will be perceived as a group. Things that look different will stick out, right? Sometimes you want things to stick out, right? There's the story of this power plant in which, the levers were so similar that it was dangerous to pick the wrong one. And then, the engineers would glue kind of beer tap tops to those levers just to make sure that they look different enough so that they wouldn't confuse them. For example, when you design a lot of things very similar, it will be a flat user interface design, and nothing will particularly stick out. If you want to make something stick out, you make it look different from the rest. Similar doesn't necessarily have to mean constant, right? In this case, we use just the exact same shape, but you could have, for example, something growing at a particular rate would also be perceived as similar. If it's a tiny triangle, a slightly bigger one, etc., next to each other, they will also be perceived as a group. So even that would work. The Gestalt law folks talk about elegant curve in this context. Right. Here's an example where this is not being used very well. You guys probably won't remember this, but back in the days, there used to be news groups. And there was a reader for those news groups that ran on the X window system, and it had a graphical user interface, but all the options, all the commands were basically mashed together in this row of buttons there at the bottom, every button has a different width here, as you can see, and there is no grouping, no law of proximity at use. There's no useful similarity of these buttons in terms of like everything being the same size so that you could easily remember where things are. And actually, to make it even worse, if you were to resize this window, make it wider or more narrow, those button rows would actually wrap around and be resorted. So every time you open that window in a different width, all your controls will be at different points on your user interface. That's not a very good idea. So, there's a bunch of ways that you could fix that, right? You could, for example, try to make all the buttons in the same width, maybe lay them out so that they are not being rewrapped when users change, make the window wider. And also maybe sort them with some distancing for groups that belong together, obviously. It's also interesting that there's like an option to exit and an option to quit, but that's a whole nother question of why that user interface is not a great one. Okay, so next one. Sarah, why don't you tell me what are you seeing here? What would you tell me to draw if I had to redraw this? You need to unmute. Yeah.
Yeah. Do you hear me? Okay. We see one curved line and another straight one, and they cross in the middle.
Exactly. So even though you could also describe this as there is this one sort of, let me show this here. This is one shape that goes up to here and then goes back, and then there's this other shape that goes up to here, like two little birds kissing. There will be other ways of looking at this, but everybody just says, I'm seeing one line crossed by another one. This is the law of continuity, also known as the law of good curve, which basically says that continuous shapes appear as belonging together, right? So that's basically another one. If you have something that continues on, we will perceive that as belonging together. And here's another law. Max, how about you? If you had to describe to me what to draw, if you had to tell me quickly what kind of shape to draw, what would you do? What would you tell me here with this one?
I would describe it as a sort of container with a thing in the middle, like half of a rectangle with something in the middle. Okay, that's still okay. You don't need to see a doctor, but it's the less frequent answer that I usually get. What I often hear people say, well, everybody can decide this for themselves, is that they see maybe a letter E or the number 3 for this, right, lying on the side. Either way, you try to relate it to something that you already know. You mentioned, a box with a divider in the middle of it, for example, which also was relating it to a concept that you already know. So we tend to file things into categories that we already know, right? That's just a technique that we do, and this means that we can use existing knowledge, which again saves us the effort of learning and memory. This is by the way, one of the foundations for the success of the use of metaphors in user interface design, right? We basically see things, and if they closely resemble something we already know, it's very easy for us to remember it. Okay, and then we have one more law. I don't think I need to ask anybody here, although maybe I do, because I want to make sure that this animation actually works. Rachel, do you want to tell me what you're seeing here?
It's Rachel.
Rachel, okay.
And I see some pixels, and some of them are moving. Mm-hmm. Not anymore.
They stop moving after a while. So what this does is basically, it's called the law of common fate. The pixels that were moving around here in this one, also called the law of common movement, you perceive as a unit, right? You perceive as belonging together. Basically, anything that's animated, especially inside an otherwise static environment, will appear as a group. So this is based on, you could also call this the tiger law, because back when you all lived in the jungle and you saw a couple of black and yellow stripes moving behind green leaves, it was very important to understand that those black and yellow stripes probably belong to something larger, which is
a tiger, or maybe a rat in the case of Bach, who knows. And so animated objects appear as a group within a static environment. And the bylaw of that is for GUI design that if you have animation, then its effect on user interface design is extremely strong, right? So here we had this, synchronous animation means that stuff gets grouped together. So even though those pixels were individual and not, didn't belong together, they were made into a group by moving in the same way. And this even works, when things are not exactly right next to each other. So welcome back to the 20th century with this wonderful example here of the blink tag in use in early web design. Somebody once said that, the guy from Netscape said that the blink tag was actually, conceived in the bar as a joke, and then an engineer implemented it overnight, didn't document it, but didn't kill it either, and that's how the blink tag got to be there. Or here's an example where this is being used in advertisement, right? So everybody sees that this is really drawing your eye, right? You can hardly avoid looking at it. So that's the strong effect of animation. Plus, you see that even though these things are now blinking sort of in an anti pattern here to each other, we perceive them as belonging together, right? Everybody sees this like guaranteed click here and the 10 pounds as one unit simply because it's animated and the rest is. All right, let's use these different things in an example. Here we have an interesting device. This is a microwave oven that has some interesting user interface features. And let's see how we can use these different laws, or how they've been used, or whether they've been used in a good way or not. Some things about this microwave are designed well, others are not designed so well. So starting with the law of experience, where do you see the law of experience at work in this one? Any ideas? I'll open the participants list here. Yeah, Matthias.
Well, obviously there are numbers and words that we know from experience to be numbers and words.
Okay, and yes, go ahead.
Another thing, from experience, we know how a number pad works. So when we see these numbers 1 through 0, we can dial in the time that we want the oven to run for, like we would dial in the phone number.
Exactly. So very good. So our experience, the number pad is a wonderful example. It's recognized because it's a standard layout of buttons, and we expect it to be used for number input in the way that it's laid out there, for example. Law of proximity. Where's that at work here? Elena, maybe?
Yes. So we have like the number block, which is approximate and down, but we have like the green and blue button, scan and defrost, and stop and cancel and add a minute are grouped together. They have additionally a box around, like not box, but circular box. So those are grouped too.
Yes. So first of all, yeah, the buttons in the number pad are also really close together, right? There's very little gaps, very small gaps between them, whereas this is a larger gap above that number pad. So that's the first one. And then you mentioned these guys. Here, the law of proximity, maybe, but if I remove these peanut-shaped circles around it, they would probably be perceived less of as, belonging together. Like the defrost and scan button would probably no longer seem to be a unit. I think the law that's at work here is the next one more so. You mentioned the lines around it, and they for sure make this like, these two stop cancel add a minute button and the defrost scan thing really belong together, right? But on a larger level, also the whole control pad is sort of set apart from the rest in this frame here. So there's more of this law of common region at work. And this is also a good example of showing, you know, sometimes the laws are used well and sometimes they're not used so well. So stop, cancel, and add a minute, I can see how those two would belong together because they're all both about, like, you know, making the cooking shorter or longer. Whereas defrost and scan don't really seem to have much to do with each other, but they're still grouped together. Probably the designer just thought he wanted, excuse me, he wanted some symmetry in his design. And finally, there's this weird thing there at the top, HC, that is defying all our attempts of making sense of it, right? It has a circle, but the circle is really small. So I'm not sure whether it's a button or not. It seems too small to be a button, and then there's like HC above that. Nobody knows what that is. Maybe, you know, high compression microwaving your food or something. We have no idea. So that's really sort of, you know, defying our attempts at making sense of the interface. Not a good design. Just for laughs, by the way, this is, you know, the scan button actually means that you take this little thing that looks like a handle, you can remove that from the microwave, and then you can scan your food barcode. And if the barcode is known by the microwave, it will automatically set itself to the right settings to, you know, prepare that food. Yeah, maybe something the world doesn't really need. But anyway, similarity, of course, also at work here. Clearly, you know, all the buttons at in the keypad that are down there look the same, and so that's giving you a super strong cue that this is a block. And it works in both ways. It's good because the numbers are grouped into one, but it also puts these other two buttons that are in the corner of that block down here also together in this thing. And that may not be the best thing, because if you look closely, one of them says power and the other one says clock. So they are buttons in order to set the clock, which you may not have looked for inside the keypad, right? In the keypad, you might more rather have expected maybe a you know, I don't know, a decimal pointer or something like that. So this is one of those cases where user interface design happened this way because there was space, right? Yeah, we still have space next to the 0, so what are we going to put there? It's the typical interface design decision, not always the best, obviously. After those Gestalt laws, we'll move on to a different topic that is about the information content in user interfaces, where we measure with computer science methods, if you like, with theoretical methods, how much information content we can actually get across in a UI. So this is not about like, how big the file is to create the UI or anything like that. It's about the actual communication channel between the user and the device, and to decide how much information can we actually get across this. So there's more about like Shannon's information capacity, information channel model that you guys may know from computer science in general. Of course, the basic unit of information in this case is the bit, right? And the easiest thing to think of that is what kind of information are we providing with a toggle button? So if the user gets a toggle button displayed, that toggle button only has 2 states. No matter how you display it, whether you make it very simple or very ornate, it only has 2 states. It's either on or off. And since it only has 2 states, the information content that the user can provide, or that the display of this toggle button can provide to the user, the information content on the in the output direction to the user is simply 1 bit, right? Because why? Well, because the log of 2, the number of states, to the basis of 2 is 1. So you could you can represent, of course, in your user interface internally that what's being stored in that user interface component within 1 bit. If you have a single digit that you're displaying in an interface, how much content does that have? Well, it's pretty simple. A single digit has 10 states, 0 to 9. So the information content that gets transferred to the user here by displaying a single digit in a user interface is simply log2 of 10, which is roughly 3.3 bits. Now this one is where you might go like, but wait, I'll need 4 bits to store that. Why 3.3? Remember, we're not talking about how much it technically takes to store that information. We are talking about how much information is being transferred from the system to the user via this user interface component. We can do another one here. If you display a single letter using the US alphabet, so no special umlauts or anything like that, and you allow upper and lower case, then you simply have 26 times 2, so 52 states, right? And that gives you a log2 of 52, roughly 5.7 bits. So a single letter with this limited alphabet here transmits about 5.7 bits of information. Measuring this isn't always easy because humans, of course, are not binary, and some of the things we'll hit in a moment are not going to be digital representations. But so far, these are, I think, pretty clear on how you arrive at the how you compute that information content. The point here in the output direction is to say these are the a letter, for example, can have 52 different values, and that's why it has more information content that it provides with a single digit than, for example, if you just show a number, right? Alphanumeric would be even more if you combined the two. Now, let's get to analog scales. Analog scales mean that we do not read off a precise value where it's fairly easy to determine the information content of the display. We are actually doing an estimate. And if you have an analog scale like the one that I'm showing here on the right, no markings, right? No tick marks on it, then how do you find out how much information content that has? Well, we basically run an experiment to determine how many different values people can distinguish on this scale with confidence. And that will tell us how many bits of information are being communicated by looking at an analog scale and taking a reading from it. If you run this kind of experiment, you find that people are actually able to differentiate roughly 8 positions reliably. And from those 8 positions of the arrow, you know, when you basically do this experiment with 8 different positions being used, every time you show one of these, the user is going to say, oh, this is position 4 or 3 or 7 or 1 or something like this. If you were to try this with 16 positions, people are going to start making mistakes, right? Because their estimate of where you are is going to, you know, start mixing up neighboring positions. So that's why we say we have roughly 8 different positions differentiable, and that, of course, then is log2 of 8 equals 3 bits of information that looking at an analog unmarked scale communicates to us. How about non-visual output? Well, we can do the same kind of experiment to determine, for example, how much information people can get by listening to a signal tone of a particular pitch. So you play back an alert tone, and it has a particular pitch. You don't do anything else. You don't use different, you know, timbres or instruments or volumes or anything like that. You just change pitch, right? How many different values can people reliably tell apart with pitch? It's actually not that much. You end up finding that it's less than 8 different positions. It's more like roughly on the order of you know, 5 or 6. It converts into about 2.5 bits, meaning that playing a, you know, pitched signal to a user and expecting them to differentiate a low pitch and a high pitch reliably every time, that's okay. That's just 1 bit of information. With 2 bits, meaning that you play 4 different pitches to a user, let's say you've got a device, you know, an embedded device that doesn't have a display, like I have a safety helmet that does that. You need to charge it, and when it's charged or when it's empty, it plays different sounds. If that was just a single pitch and it was 4 different pitches that was using for different communication, that would all already kind of stretch the limit of what I can reliably distinguish and perceive. But Some people have perfect pitch, so they can actually tell, oh, that was an A flat in the 3rd octave, right? And if you have that ability, then of course, all of a sudden, you can distinguish 5 to 6 bits of different notes, because you can basically tell down to the half note of where you are, and you've got all of a sudden, you've got the range of, you know, a good part of a piano, right? And just to add to that, you might say, well, what about volume? Can I not use volume instead? Isn't that going to be better? Actually, we're even worse at distinguishing reliably different levels of volume. Now, that doesn't mean that you have a trouble hearing a sound, and then when it gets softer or louder, you can tell exactly what's going on, right? That's super easy. But what I'm referring to here is if the system was trying to communicate to you different kinds of information based on how loud it plays a song, you know, like a simple sound. So a soft sound and a loud sound. Once you go up to 4 different levels of volume here, you're already reached the limit of what the average person can actually reliably distinguish and identify. And maybe identifying is the better word here than distinguishing, because I really want to be able to say this is volume number 1 or 3 or 0 or something like this. Well, and finally, this may not be the perfect user interface, but imagine you had a widget that you would have to kind of lick in order to check whether you got new emails or how many new emails you have. Okay, so it's a licking interface, and we can imagine that you can adjust the saltiness of this licking interface to communicate information. I know, not the most hygienic interface, especially in times of Corona, but hey, just for the sake of argument, how many levels of different saltiness can we distinguish reliably and identify reliably? It's even less, 1.8 bits. So we cannot even distinguish 4 different levels of saltiness reliably when you run this experiment with people. So saltiness, probably not the best user interface modality, apart from the hygienic concerns. A question that often comes up is, should we use an analog or digital display of information? And I want to talk about a few of the things that are pros and cons about this, but I don't want to just break those to you. I would like to gather some suggestions. So let's take an example. You have a speedometer in the car, right? The Tacho in German. So that's telling you how fast you're going. I would like to hear some arguments from you guys for either an analog scale, that displays the speed with arrows, with the pointer, a needle, or for a digital display. Fabian, go ahead.
I actually prefer a digital one, because if you actually have like just the kilometers per hour numbers, that's totally sufficient. Any information between like 96 or 97 kilometers is pretty much useless to the human.
Okay.
And it's totally sufficient, and you can probably you probably don't make mistakes just because of the scale if it's digital and it's in steps of 1 kilometers per hour or miles per hour or whatever.
Okay, so here we have the pro digital scales person. Elena, I hope you are going to argue for analog scales so we can have a fight.
Of course. But if I have like an analog scale, I can see like my max, so I can procentally watch at which state I'm at. So I think that's a big pro.
Very good. So the scale will tell you like how far it apparently seems to go. So that's one advantage of an analog scale, if that maximum on the scale actually represents the maximum you can go, right? But yeah, even if it doesn't represent the maximum, maybe seeing that you are in this first half or second half is going to give you a quick at a glance information. All right, Umar, what do you think?
Maybe because you're used to look at the watch, you know that the middle up is 12 o'clock. So if you look at your speedometer and there's the 100-kilometer mark, you already know when you hit the 100 kilometer without really looking at it.
Okay.
So you
interesting.
just need a quick blink, and then you know, okay, I'm at 100 or 97.
Very good. Yeah. So that quick, like, glancing over kind of thing seems to be something that the analog scale may support better. And of course, I have to ask you, Jan, as well.
Does it work?
Yep.
In my opinion, the digital scale is better because we only have to look at like the 2 digits which are displayed, while the analog one is always a bit you cannot label every single point, so we always have it in like 10 steps. And that is always then if you want to go like 55, then you then it's really annoying to always see, okay, now I'm let's say half both. And a further problem which is in cars, at 100 it goes in 20 steps. So if you change scale in the midst of it, then it gets really annoying, because the speed limit is 110 and you are used to go in 10 steps per point, and suddenly it changes to 20 steps per point. Then if you are not completely there because you're tired or something like that, then it could happen that you drive faster than you should.
Okay, so a change of scale on the scale, of course, that's not very nice, because that breaks our sort of quick at a glance thing. Alvina, because you got your hand up, but we got to be quick now so we can move on. So let's hear what you think.
Yeah, I'm also in the support of analog one, because in the analog scale we can also define ranges. Like, for example, we are often got to hear on some road, like, or see the banners like you have to be in the speed limit between 50 to 70, for example, or 50 to 60. Then in the analog scale we can see it in a glance.
Okay, so we can nicely see whether we are within, especially 2 tick marks on the analog scale.
Yes.
Wonderful. I couldn't have arranged this better if I had, rigged this whole discussion, because we had pro digital, pro analog, and in the end, we got pros and cons for both, right? So the analog scales tend to have an at-a-glance capability. If you imagine you've got a display with lots of indicators that are all like little gauges, you could probably quickly look at them and see if any of them, for example, entered the red area. That is easy to do on an analog display. Range limits were being mentioned already. One thing that you guys didn't bring up yet is trends are actually very nice to see, because human perception is wired to detect movement, right? We are really going to react to movement very quickly. That's how our eyes work. And so if you can very quickly tell whether your needle is dropping slightly or increasing slightly. So for those kinds of things, the analog scale has certain advantages. But if you want to get more precise, as somebody was mentioning here in the discussion, it gets hard, right? If I want to know, am I going 53 or 54, if that's important, then that gets hard, right? And I need to really peer at this analog scale, or may not actually be able to tell that. So in the end, it really depends on the use case, right? What is the use case for what I'm doing in the car? Is it important whether I'm going 53 or 54? Probably not. So you have to know what kind of use case you are looking at. And so once, if there was ever a speed limit at 57 introduced in some crazy country, then that would really mess with lots of analog scales, because nobody knows, am I going 57 or not? Digital digits, however, have an advantage. Up to 3 or 4 digits, we are actually basically finding experiments that they have essentially constant readout time. So we can actually read a 3 or even 4-digit number in the same time we can read a 1-digit number. We're really fast at that. It's just estimating, is this, especially if it's a 4-digit number, is this above or below 5,380? Kind of hard to tell. You have to really look at the number and compare it. Trends are a little harder to detect, and limits are not going to be visible unless there is an external labeling of some sort. Okay. Now, with these things out of the way, we're going to move on to this book here. But before we start with Norman's book, I want to talk about a few more things that have to do with HDI literature. Where can you learn about human-computer interaction? We're going to go through this book by Norman here, but I want to show you a couple other sources you can tap. First of all, HDI is a fairly young field that's been around since roughly the 1980s. As a really evolving field along with computers and the PC revolution. And so there is a lot of conferences and journals that you can find online. The biggest conference in the world, or the most impactful in the world, where the top research gets published, is called CHI, or CHI. And that's the main conference on HDI research that has the sort of the most impactful papers. And then there are other conferences that are really good, but that are more focused on particular areas. Like WIST is, for example, user interface software and technology. It's more technical. DIS is a conference that is about designing interactive systems. It's more about the soft aspects of the design process. The Interact conference has a strong Euro-Asian basing. CCW is more about group work, computer supported collaborative work. UbiComp looks more at ubiquitous computing, which we'll talk about later in this class. So the installation of sensors and actuators and devices all around us in our world. And then there's a conference, related conferences like the ACM Multimedia Conference. So there's a bunch of those. Journals also, Tokai, Transactions on Computer-Human Interaction is the most important journal. It's an archival thing where you will find papers or articles that will last for 5 to 10 years maybe in terms of their validity. Interactions is a very nice magazine if you're interested in the business of HDI, how this is getting used in industry, what practitioners are talking about these days. For example, big discussions are going on right now in the Interactions magazine about how are we going to interact with artificial intelligence, for example, and artificial agents and stuff like this. PUC is another journal that is basically publishing the results of the UbiComp conference in a journal format. Where do you find these? The best way for you to find most of this work is actually the ACM Digital Library. ACM is a professional institution that is basically like the union of computer scientists all over the world, the Association for Computing Machinery. It's similar to the IEEE, but ACM is more on the software side of things. And it's a very big society that supports most of the conferences and journals that I've mentioned up here. So you will find them in their digital library. Usually you have to pay for access. You have to be a member as a professional computer scientist, but you guys are lucky, you work and study at RWTH Aachen, so we have an institutional free access to the ACM Digital Library. So make good use of that. You have to create a free account and then log onto it from inside the VPN from RWTH, and then you can actually connect to it, I think, for half a year. Even without connecting to the VPN, it'll remember that your account is associated with RWTH before you have to identify via VPN again. Conferences tend to have papers that typically are relevant for like a few years, like 1 to 3 years maybe. Journals tend to have maybe, I would say, 3 to 5 to up to 10 years, and books are usually trying to be even longer lived, of like 5 to 20 years of sort of lifespan of being relevant. And typically in conferences you build on what you published last year, for example. That's why they are more short-lived in their nature. Talking about books, the book that we're going to go over is called Design of Everyday Things, the revised and expanded edition from 2013, in which we will talk about, you will learn about affordances, mappings, constraints, the 7 stages of action, visibility, etc. So a lot of the concepts that we're talking about in this class, in the first part of this class, are covered in this book. This book is required reading, right? You need to read this book. We expect you to know what's inside this book. There are 2, maybe 3 actually recommended readings. We're not going to ask you about details from these readings in the exam that we haven't covered elsewhere. But the book by Alan Dix and colleagues is the best single volume textbook on HDI as a field of study that I know. So that's definitely worth getting. But we will also point you to the library, and we'll have excerpts of these of chapters available for you to take a look at. Schneiderman's Designing the User Interface is another one that we recommend. It's more practice-oriented and has great overviews of different technologies. If you want to understand what's going on with voice in the user interface these days, his book is a pretty good one. And I believe there's actually a newer edition out there. Ollie, I think the last one is from, isn't that 2016 or something? Yeah, we can update the slides. Never mind. And the usability engineering book from Nielsen is really old, but it really explains nicely how usability can be brought into the business and how it can become a part of the business, which is what many of you guys who don't join research later on are actually going to be doing. Right? You're maybe working on user interface design. You may be the head of usability in a company, and you have to bring usability into the business, and that's a hard job to do. And this book has some hints on that. If you want to know more about good books in HDI to read, I recommend taking a look at my list of HDI books. I keep updating this to be sort of the top 10 list of books that I think people should be taking a look these days if they want to learn about HDI. And it has more details on each book as well. Right. So finally, the book that you're going to be reading, I want to explain how I would recommend you read it. And that's actually how I recommend you read any book that you are reading for class. And most of these things I think you are aware of already. You've studied for a couple semesters, so you should know this process. I just want to reiterate. If you read a book, do active reading. So take this book, take a marker and start highlighting things. And not every sentence, right? That's useless, but 1 to 2 key points per page at least, so that you make your brain think about what you're reading. Scribble brief summaries in the margin, right? If you think you've understood a concept, then write it in your own words, right in the margin. Make exclamation marks where you think something important came up, or a crazy association that says, wow, this example of bad usability really reminds me of my student dorm door, or something like that. If you have a cool project idea and you read about, oh, visibility in smartphone screens is bad, and you have an idea on how to fix that, write it down, right? So use the margin to make this book your own. Put tiny little sticky notes with keywords onto pages that you keep referring back to, right? So it's really helpful to have these small sticky notes and just stick those into your book and some page and write down something on there so that you can then go back to it like a bookmark to find stuff in there. So what I'm trying to say is make this book your own, right? Also, in a separate document, I recommend writing yourself short bullet point summaries of each chapter as you read. It really changes the way that you learn, right? We know that if you just read something once, you haven't learned the material, right? You need to engage with it. And writing yourself a short, my summary of this book, maybe even in your native language, for example, in German, if you're from Germany, can help, because the translation and rethinking process also helps you to really use your own words to write down the things that you've learned. You'll be surprised at, all of a sudden, oh, wait, I need to actually understand what affordance means so I can express it myself. And that's exactly the kind of thing we're going to be expecting from you in the exams, whether it's oral exams or the final written exam in this class. A good way to tell if you did a good job is you should be able to tell your copy of the book apart from everybody else's copy of the book from, like a 10-foot distance. This will increase the value of the book for you many times. So don't consider this pristine, right? Go crazy with this book. It's learning material. You're supposed to make it your own and make it so that nobody else will be able to say that it's their book after you're done with it, right? So don't just read it, use it. I've got a picture here from one of my PhD students. One of the reasons we hired him, because he went, he was an exemplary student in DIS1, as you can see here. This is how he marked up his book, right? And going over it during the course of the semester, and then in studying for the exam and stuff. So he has super indexed this book, right? He will be able to tell whether it's his copy or not. Okay, so with that out of the way, the design of everyday things. Here's a picture of Don Norman these days. He's still super active, heading a design lab at the University of California in San Diego, where he's worked for a long time. So he's in Southern California now, but he's worked in the Silicon Valley for a lot of his time too. The Design of Everyday Things is a book. By the way, this thing you see here is sort of his, example of a designed object that is intentionally unusable, right? You never could, pour yourself a tea with this. And my students, when I turned 50, got a local guy to make me my own version of that wonderful unusable teapot in honor of Don Norman's work. So this book got originally published in 1988, and it was called The Psychology of Everyday Things, because Don Norman is really a psychologist and a cognitive scientist, and coming from an engineering background and not so much from a design background. But he found that nobody buys a book with that title, so he changed the name shortly after, and I think in '92, called it The Design of Everyday Things, and then it started really selling. It quickly became one of the Bibles for HCI. I don't know any HCI researcher who hasn't read this book, right? So this is why we make you go through this book in the next couple of weeks as well. It got significantly revised and updated in 2013, and that's the version that you guys are getting and that you will be reading. One of the things that this book introduced to the HCI community at large was the concept of affordances, which we will talk about today. But Norman did a lot of other books and later on, and so he has a whole series of additional books here. I won't go into much detail about those, but he's continued to write books on the topic of HCI. So let us jump into the first concept here in HCI that Norman introduces. And it's called visibility. And I'm going to give you my own twist on that so that you have a little bit of extra information, not just what's in the book. Before I get started, just a quick sanity check. Marcel, Ollie, you guys are keeping track of the back channel. Anything we should bring up to the forum, or are we good?
Yeah, maybe the one question whether you should read the book from basically front to back, or whether we give you chapters. I don't think we will give you chapters. Actually, it's a pretty easy read. You can read it from front to back. You can mix it up. I would just say once or twice a week, get a cozy cup of coffee, get yourself in your couch and just read it a bit and see whether you can find the content that we already covered in there and read more up on it.
Yeah, I would also really recommend for this one just to go cover to cover, starting at the beginning, because actually some of the concepts build on earlier chapters, like, you have to understand what affordances are and signifiers before you get to the other chapters. So yeah, not selected chapters. This is a book that you start reading from the cover and then just keep going through. We'll give you a rough reading estimate for what you should be covering this week at the end of this class. All right, so visibility. Here's a short video that shows a wonderful comment from a guy who runs the webpage webpagethatsuck.com. Okay, I'm going to just play that with the audio commentary and let you listen to it.
It's not just small companies or music sites or band sites or sites that really don't count that use mystery meat navigation. Even big companies go stupid sometimes. And here's an example, Qualcomm. If you look up here in the right-hand corner, you see the mystery meat navigation. You have to mouse over this thing. Oh, now you can see what it does. Oh, okay. This is the latest news, and this is Ventures, and where was CDMA? There it is. People are not going to memorize your navigation. This isn't very impressive, except to people who should know better. Don't use this technique.
All right. So a good example, I love the name mystery meat navigation. Mystery meat is what you find in your burger when you don't really know where the meat is coming from, right? So this thing is hiding the information that you're supposed to find. Why is this page so, why is this website so hard to use? Because we're missing the visibility of these different menu items, they're made intentionally hard to see, which is a bad idea. So visibility is based on the fact that the mind is really excellent at noticing and interpreting clues in the world, rationalizing about them, explaining the cause and effect behind things. We do this all the time. This is why much of the knowledge that we think we have in our head is actually not in our head, it's in the world around us, right? I don't need to remember all the details of how this pen works, because every time I look at it or I look at a new pen, I see so many clues about how to use it so that I immediately know what to do. I don't need to have a session on how to write with a ball pen and which is the pointy end that writes, right? But in order for this to work, these things need to be visible, right? I need to be able to see in the larger sense of visibility. This could also be by tactile, feeling things or something like that. I need to somehow be able to discover what the things are that I can do with an object. Ideally, you would have clues, that are natural to the object and they are made visible. And I don't even need to think about what I want to do with how to use the object, right? I just pick it up and it naturally works. I got my scissors and they've got these holes in there, and I know, okay, this is where 2 fingers fit, this is where only 1 finger fits, and okay, and obviously I'm not going to touch it on this end because that's pointy and sharp. So super easy to understand what to do. I don't need to think about this. So visibility is important, but excessive visibility, of course, is bad as well, right? You don't want to show too much. You don't want to overload your user with information. That's a problem of highly complex interfaces. Often they just throw everything at the user and then you have to sort through it. That's just as bad as the lack of visible clues. Let me start with an example here of what has become known as the Swedish hairdryer. This was a hairdryer I found at a conference in Sweden, maybe in 2001 or 2002. I traveled there from Stanford, and we had a conference there with our Swedish partner institute. And my first reaction when I entered the hotel room and saw this hairdryer, I was like, ah, that looks really cool. But then I picked it up and looked at how to operate it. And so I have a few questions to you guys. First of all, what do you think you would have to do to turn this thing on? I'm just going to ask a few people. Max, what do you think? How would you turn this thing on?
I would suppose you have to turn it.
So turning sounds like a good idea. I'll ask somebody else. Annika, maybe?
I would try and push it upwards or downwards.
Okay. We'll ask Tejaswini, Shinde.
I think you'd probably have to press and hold it throughout the
Lovely,
duration.
thank you. Jesus, it's like I'm rigging these discussions. No, literally 3 people, 3 different answers. Isn't that amazing? Guys, this is just a hairdryer. Like, what are we doing? We're discussing how to operate a hairdryer? That's nuts, right? This is bad design. This shouldn't happen. It should be perfectly obvious how you use this thing. I've got another question for you. How many levels does this hairdryer have? Lucia, what do you think? One?
Sorry,
Two?
I was just writing something in the chat because of the book.
Okay.
I think levels none.
No levels. It just exists. It's just there.
I think that maybe you can put it on and you can put it off, and you can't really say if it's warmer or faster.
Okay, so on and off, basically, just this one level of onness, so to say. Possibly. Anybody think there's more levels? Ezra, what do you think?
Yeah, I think the highness of the levels depends on how much you push the button.
How much we push. Lovely.
Yes.
Okay, totally wrong, but I love your guess. It's wonderful because it's showing how bad this design is. So We don't know, right? Again, it's a hairdryer, Jesus. And I'm going to show you something else. Those who said you need to push this thing up were actually right. So I have another question. When you find the hairdryer in this state, do you know what state it is in? Can you say for sure whether it's on or off? That's kind of an important question for a hairdryer, right? You don't want to like pick it up with wet hands if you think it might actually be on. I mean, normally you hear your hairdryer going, but let's assume it's broken. You want to know whether it's actually turned off, right? So that is also not easy to say, right? And what do you think? How would you go to the next level now that we've done this? That's it. That's easier though. Jan Niklas Forro.
Well, actually, I know the answer because I've seen your TED Talk.
Okay, that's great.
Yeah. Should I say it anyway?
I'm going to show it on the next slide then. That's all right. So you don't count because you watched the TED Talk. Thank you for watching that. I appreciate it. But Artem, what do you think?
I think it's state on and 0 off.
Right. So it looks like it's currently in state 1, so it's turned on at level 1 now, right? And if there is a level 2, how would you get to it?
I think I will go push it down, and maybe on other side of this roll you can show other number maybe.
Yes. So that is actually how it works. But you know, be honest to yourself, everybody. How many of you would have tried that as the first attempt, right? So if you wanted to switch this to level 2, you actually have to go back to 0 and over to the other side, and that's where the 2 is hiding. All right. That is so broken, right? Why am I talking about this? Because this is fundamentally, there are several things wrong with this, but one fundamental problem here is visibility. When you encounter an object as a human, you ask yourself 3 things. First of all, where am I? What is the current state of this thing? Right? So state is what you want to see. And we were not perfectly sure, like if you find this hairdryer in this state, would you know whether it's on or off and in state 1 or 2? Maybe it's in state 1 because that's the one we're not seeing. You know, you don't know. So the state is important to see. The second thing is, what can I do here? Actions, right? And again, when I found the hairdryer in its turned off state, I wasn't sure how many levels it even has, right? And that's bad design. It doesn't tell me about its available features or functions. And the third thing is, how do I do it? And even that was unclear. Even if somebody told me this thing has 2 levels, it wasn't obvious how to get there. Right? So what's the state? What are the actions? And how do I get there? Those are the things that people ask themselves. And all these questions are answered badly by this hairdryer design. Now, if you were to improve the Swedish hairdryer, does anybody have a suggestion on how you would fix this design? Fabian, go ahead.
Yeah, maybe I would make a little. First of all, I would make the scale from 1, 2, and from 0, 1, and 2, maybe to the side, and then put a little arrow on the current one. It doesn't look as stylish, but I mean, you could figure something out if you wanted to implement that in a little bit more stylish way. So you have a little arrow always showing the actual state, and if you can also see states 1 and 2, you might think that turning the ball would be the thing to actually put in that state.
Exactly. Right. So that you made an important distinguishing point here. The first thing to do, and that is a fundamental rule really that applies to buttons and toggles everywhere. If you want to be perfectly clear, you need to detach the labels and the control. Meaning you would have to have a 0 and a 1 and a 2 printed somewhere on the casing, and a slider that moves either to the 0 or to the 1 or to the 2. And then it's super obvious where we are. It's super obvious what levels are, and it's super obvious how to get there, right? It's simple. It just maybe doesn't look as sexy, but you want to make sure that these things are usable. Another thing is also, you may be using this hairdryer behind your head, so and you want to be able to easily turn it higher or lower. So again, a natural ordering of like off level 1, level 2 is also going to be helpful in that respect. We're going to get back to that question of natural ordering, natural mapping in just a few minutes. So you want to know, what can I do? What are the possible settings? I want to see how many settings are available. I want to design the knob to show how it can be operated, right? The knob should have a design that suggests to me how to operate it. And that has to do with affordances, which we'll talk about in just a second. And I want to make sure that the current setting of the control is easy to determine against the scale, right? Where am I? Finally, if you want to really do it well, you want to do a natural ordering of these settings from 0 to 1 to 2. If this is all fine, if the product is new, but you have to design it for use, right? For example, you have to think about that people are going to be operating this in one hand. So the switch has to be positioned in a way so that I can operate with one hand while I'm using the hairdryer. The labels must not wear off, or otherwise it's going to be useless after 3 months of continued use. The control should be water resistant so that I don't kill myself. Then maybe you need voltage settings so that it works in different countries. So all of these things have to be kept in mind when you design something like a hairdryer. And fundamentally, in the end, you want to apply always the first rule of user interface design: keep it simple. Right? Don't make it overly complex. When we talked about this with students one year, a student suggested, well, why not have a voice-controlled hairdryer? And I was like, that's a terrible idea. Right? Imagine the noise that a hairdryer is making when it's turned on, and how are you going to do reliable voice control? If somebody walks by and says, supercharge, and then suddenly your hairdryer starts setting your hair on fire. So keep it simple, right? Don't over-design, don't over implement things for something as simple as a hairdryer. Okay. So that's about the hairdryer and visibility, right? A lot of this is about showing the user what's available, how do I get there, and what's the current state. If we don't have this, we start still, because the brain is wired that way, we still try to make sense of things, even if the clues are not given. And that often leads to false assumptions. If you have a lack of visibility and there's some coincidence, you may create a false causal, cause and effect relationship in your head, thinking that your action had no effect or maybe a bad effect. As an example, when you get your parents to get online with their phone, with a smartphone or something, and then they launch one app, and by chance at that moment, the DSL router stops working, they will never launch that app again, right? Because they assume that it was the app that broke the internet, right? So we are built to make sense of cause and effect relationships in our world. And if we don't see clearly what's going on, we're going to build false cause and effect relationship and then use things in this way. When this happens, it actually leads to superstition and a certain loss of control over technology that surrounds us, which is bad, of course. And you've probably been in this situation as well, right? So you try to open an app or something on your computer, you click on the link, nothing happens. After like a second or so, you click again, nothing happens. After a few more seconds, you click many times, because that's surely going to help, right? And then at some point, all these events that got stacked up by the system then suddenly get processed, and then chaos ensues because your clicks go into places where you didn't want them. We have this assumption that things, when we don't get the visibility of the state and the feedback of what's happening based on our actions, we tend to just get into operation errors. And I know people who, I know this, I'm not sure whether you guys still know this, but people tended to burn CDs and DVDs in their drives, and then sometimes People would gently put their hand on their laptop to make sure that it wouldn't shake in a particular way when you're burning a really important CD. You know, all these superstitions get created because we don't really know what the process is doing and whether what we do actually has an effect. Now, there's a problem with this, you know, usability in general, because usability isn't automatically a business goal, right? And consumers will have to actually prioritize usability before the industry changes. And that's actually gradually happening. I've seen that happening over the last 10 years or so. People are beginning to pay way more attention to the usability of products than they did before. It's kind of, you know, it's scary to think about the fact that we're facing an issue that Norman first writes about in 1988, and we're still facing technology that is hard to use, even new devices that get on the market, right? On the one hand, it's a problem of the designers and the product makers, but in the end, they are serving the market. And as long as people walk into the media market and buy things only based on the list of, you know, how many items are on that bullet list of features for this thing and how much is it costing, we don't have a clear sort of, you know, preference for usability in the consumer market. So my goal for this class is to turn you into really kind of, you know, cranky nitpickers, right? You will be walking around and you will always say like, that's a bad design, that usability sucks. But hopefully you also see good design when you encounter it and good usability. And you will encounter these issues everywhere in your environment, right? You can tell that companies are gradually catching on to this, because Philips, who used to have a really lame tagline, let's make things better. Like, that's a great tagline. What's the alternative? Let's make things worse? I don't know. Anyway, they actually changed to a different tagline, Sense and Simplicity, where simplicity in design already made it in there. And our latest one is Innovation and You. And that's sort of showing this user-centered focus of products, which I think is actually a good development that we're gradually seeing in the industry at large. So I think this class will do that to you, and it will change the way that you think about technology. And hopefully, when next time you enter MediaMarkt, you won't be wondering about like how many features can I get for 100 euros, but what's the usability that I can get for 100 euros, like when you buy a product. Or, you know, online is the same story. I had this epiphany moment when I walked into MediaMarkt one day, and I heard people talking about new smartphones in the next hallway, in the next aisle down, and they were discussing things like, oh, that looks like an awesome design. Well, but wait, you know, that there's no visibility of how you get to this feature, and look, they completely ignored the Gestalt laws of proximity. And I was like, wow, awesome. I walked around the aisle, and sure enough, it were two former DIS1 students that had taken our class. So on the one hand, I was like, oh man, it's sad that not everybody is thinking like that, but at least, you know, once people took this class, they have this understanding, and hopefully you can share this with others. And to wrap this up, this part, you know, here's a great Dilbert cartoon that catches that problem of, you know, relaying usability to other people. Your user requirements include 400 features. You realize that no human will be able to use a product with that level of complexity. And then what happens is that, well, I just better add easy to use to the list. That's not how it works. Unfortunately, we'll have to do a little bit more to create usable products. And also, this is a warning of what happens often, which is that usability is being considered way too late in a project. I've been brought onto countless product designs by companies and even by corporations and public institutions who ask me to help with the usability as a consultant. And you come in and basically they're done, right? We're all done. Can you make it usable now, right? That's not how it works. You need usability to be a process early on in the beginning of your project. And that's something we're going to talk about in part 3 of this class, how you make usability part of your design process. But let's poke some more fun at RWH technology, right? Here's this desk phone that I've used until about a month ago. We now have new ones. And this desk phone has been with me for like 15 years. Look at this desk phone carefully, and tell me what button you would press to check your voicemail. Any ideas? We drag over the participant list here. Victor, go ahead.
I would vote for the mail button.
Yes, I'm going to zoom in on this. Down here, there's 3 buttons, a mail button, and these other 2 buttons. So that looks clearly like how you would call up the voicemail, right? No, it's much easier than that. All you have to do is dial *71. Isn't that great? I love that, right? So yeah. This is where it's actually worse than not giving you a clue, right? It's actually giving you a wrong clue. When you push that button, nothing useful happens at all. Instead, you have to, look up the online manual and find out that this is the cryptic key combination you have to type in to actually get to your voicemail. And I think that's a wonderful example of visibility having, gone completely wrong. This is actually worse than not giving you any clue. It's giving you a wrong clue, right? There are more issues with these phones. For example, when you call like a company and it says, please press, 1 to do this or 2 to do this, it doesn't work by default. You have to dial *8 to activate tone dialing. If you don't do that, then you'll just be disconnected from the call when you press the first button while you're in the call. If you ever miss the call, you can retrieve that number and look at it, but you can only see it once. If you go back, it's gone. You can no longer retrieve it. That, by the way, also has something to do with the privacy considerations of the HR representation of the workers at RDPH, who were concerned that if you were able to bring back caller lists for a longer time, it would be a problem. And there are more issues like that, right? Mobile phones, before the advent of the smartphone and its full screen touch screen, were actually not much better, right? And even today, if you wanted to activate a caller ID blocking on your phone, which is a network feature you have to talk to your provider too about, it's often hard to find these things. So now we're going to show you something that will take us to this important concept that Norman calls affordances. And it's about these British Rail shelters. So, they're like bus stop waiting booths that British Rail built up. They created these with glass walls, and they were being vandalized and broken routinely, right? People just kept smashing in these walls that were made of glass. Why? Well, on the one hand, because people were not being very nice, but also this glass, as the designers of these British Rail shelters realized, was suggesting that it is fragile and that would probably be a really cool effect to shatter it, right? So the glass was almost suggesting that it could be broken, right? Or as we say with Norman's words, glass affords, it has the affordance of breaking it. It suggests that action to a user. So British Rail redesigned it. They replaced the glass with equally strong walls made from plywood, Sperrholz in German, and the breaking of these glass walls stopped. Nobody, kept breaking these walls, although it would have been just as easy to kick in this plywood wall as it would have been to kick in the glass wall, because the wood, by its looks, actually suggests and affords more of a stability and a support. However, what happened now was that now these walls were being scribbled upon, because the smooth, even surfaces of these plywood walls were really great, as drawing backgrounds and as canvases to leave graffiti. So the smooth, even surface, single color, actually affords drawing. This leads us to the concept of affordances. Affordances is one of the models that Norman introduces in his book that you guys are going to be reading. And he got this term affordance from a researcher who worked in environmental biology. And he called this affordances, he used the term to describe the things that an environment offers to a person or even an animal. So the natural features of an environment that it suggests to an animal or a person to make use of. In our case, in Norman's reinterpretation of affordances for user interfaces or for interaction with technology in general, affordances are the actions that an object allows the user to do with it. To quote Norman's book in the revised edition here, we've updated this, an affordance is a relationship between the properties of an object and the capabilities of the agent in our case usually a human, that determine just how the object could possibly be used. So a couple of important things here. First of all, an affordance depends on both the object and the user. Norman has a nice example in his book. A heavy chair, of course, suggests to sit on, and everybody can do that. But if it's very heavy, it may suggest being lifted, but not by a young or weak person, right? For that person, the object, the chair, a heavy chair, does not afford lifting. It only affords sitting on it, or maybe standing on it. Second thing that's important to understand is, so affordances are not just properties of objects. They are always properties of objects in relation to a particular person or a group of persons. The second thing is that affordances can be visible or perceivable, as Norman calls it, or they can be hidden. So this is the important thing. You can have an affordance that you can clearly see, like a chair lets you sit on it, and it also suggests that you sit on it. It's visible, right? Nothing hidden about it. But some affordances may be hidden away, and in that case, we have to do something to make that affordance visible. And that's where the second concept of Norman comes in, which is called signifiers. A signifier is a signaling component of an affordance. So the signifier signifies the affordance. To put it simply, you could say an affordance is the list of, what kind of actions can I do? And especially if you have something, for example, like a modern touchscreen or something, a touchscreen affords touching, right? The touch surface, we've learned, is something that we can touch with our fingers. But the signifiers then illustrate where we need to touch and how we need to touch and how we need to swipe or tap or something in order to reach certain effects. For product designers in graphical user interfaces, for interface designers, signifiers are actually the more important concept, because in most cases, the physical affordances of something are already determined. It's a device, it has certain features. And so you are left to use signifiers to indicate where and how to use the device. Sometimes we're lucky. There are many designs, especially in everyday objects around us, where the affordances are actually perceivable. You can see them, like in the example of the chair. I don't need to put a sign on the sitting area of the chair saying sit here, right? I don't need to label my chair that way, because the chair, by its natural shape and what we know about our bodies, just invites us to sit on it. So it has the affordance to sit on it, it lets us sit on it, and that affordance is visible or perceivable, so we don't have to put a label on it to explain it. That usually ends up being the most easy to use design, right? If you have an affordance in an object designed into it and is perceivable by the user, you don't need any additional labeling, any additional signifiers to explain it. But in many cases of a graphical user interface that we're mostly going to be working on in our field, you actually have to have signifiers to explain where and how to use the fundamental affordance of, for example, a touchscreen. Okay, finally, signifiers don't have to be visual. They could also be sound emanating from a particular location, or haptic, button ridges that indicate where I can find the button. On my PS4 at home, I always, in the dark, struggle with finding the on-off or the eject button, because it's perfectly designed into the front panel without any, ridge to feel it. So that's missing the signifier. It's also not colored, so you cannot see it. So that's an example of not providing me the right signifiers to find it. Okay, so only if I have an affordance that is not perceivable, then I need to add a signifier to it. That's sort of the basic story here. And we have this example here on smartphones. Early on, the unlocking happened by sliding sideways on the touchscreen at the bottom here, and that's being indicated with, or was being indicated with this little highlight animation that was sort of suggesting to us how to operate it. That's clearly a signifier telling us what to do, because that was not something that you could have perceived from the device just as it is. Now, most signifiers are usually intentional when we design objects. For example, any sign really that tells us how to operate something. For example, a door sign that says, push in order to open. Or any buttons that say, click here, any labels on buttons that says click here. Those are all intentional signifiers, because we found that the affordance is not by itself perceivable, so we need to add that explanation of a signifier. It's not, a coincidence that these signifiers sound like sign, right? A lot of signifiers are simply small signs. They also can be unintentional or accidental. For example, when you walk along a snow path, along a snowy hill, and you see this footpath that others have created in the terrain, that was not intentional by them probably, but even though it's accidental for you, it suggests, oh, that seems to be a way where you can walk safely to get from A to B. Or if you have a flag, you look outside the window and you see a flag, and you use that flag to indicate the wind, to read the wind direction. It doesn't matter whether the flag was there, as a, like at an airport, it was placed there in order to indicate wind direction, or whether it's, some kind of other decorative flag that just happens to indicate it. It doesn't really matter in both cases. We use it as a strong cue. So affordances and signifiers are really meshed together closely. I really urge you to read that section in the book of Norman carefully. And how we use them for design is basically, if we can find a perceived affordance, so we have an affordance, it's one that we want to encourage, and it's perceivable on the object, then that's a really wonderful, strong clue, right? So that is the best way to go. We don't need extra signifiers. So when you see a design that has to use labels in the physical world, especially with simple devices, that often indicates a design that could have been done better. Right? So there may have been a way to actually use a perceived naturally available affordance of the design, of the product, in order to indicate how to use it, rather than having to label it. In software user interfaces, that's often also true, but many more complex, more abstract functions in modern software UIs will usually need signifiers. What I mean by this is, it's hard to sculpt a device in a shape so that it suggests that you need to push here in order to, format your text in Hebrew with right side indentation and alignment, right? That's a complex function that is not easily cast into an affordance. So typically we find signifiers in software user interfaces used a lot. And that's why they are really important for us when we design software interfaces. In general, product design can support usability when you use perceived affordances and signifiers in a good way. All right, so here's an example that I actually found myself one day. I bought this headlamp. No, that's not true. Somebody gave me this headlamp in a class in DIS1 years ago because he thought it's so hilarious. And so, how would you turn this headlamp on?
Jan, there's also a question by Selina, probably.
Oh yeah, Selina, go ahead. Go ahead first before we get to this.
I've already got this answered in the chat, so I'm sorry.
Oh, all right, good. Selina, Rachel, go ahead.
I guess I have the same one, but I would push the button on the top.
Ah, good. Okay. So let me give you a different angle on this thing. That's actually not a button on the top. That's it just looks like a button, but it actually isn't. So great answer, because it already shows we're going to try something else. What are you going to try next? If that doesn't work.
If I was supposed to answer, then maybe turn the thing on the side.
Yes, exactly, because there are these little wings right on the side. So that looks like turning. Let me show you what these are for. This is not how you turn it on, by the way. So if you try to turn on one end, on the right-hand side here, you will find that it doesn't work. It's just latched on. It's glued on. And in fact, the designers apparently found that people broke this lamp by trying to turn this with all their might, and they put little labeling there, don't twist, right? Which you're going to see probably after you broke your lamp. It's even more fun though if you try turning on the other side. Let's assume you are, climbing a mountain and it's getting dark and you've got one hand available, you're wearing your headlamp and you're going to twist this other side. What happens then is you're going to open the battery compartment and the batteries are going to plunge into the abyss below you, and your headlamp is going to be useless and you're going to be without light. So turning on one side doesn't work. It's not available. It's, even though it looks like it would be available, you can't do it. So that's a false affordance, right? You would like to twist it, but you can't actually. You can't operate it. And then on the other side here, where we have this, this thing, you can actually. So it has the affordance of twisting. Great, you can twist it. So the affordance in itself works. It's just that it doesn't do what you expected it to do. So your mental model of this thing is wrong. And in fact, it instead does something quite drastic, opening the battery compartment. How you actually turn on this headlamp is to press this unsuspecting little black area at the very edge here of this lamp. That's the push button that you need to push to turn on this headlamp. Give you another example, straight from Norman's book. How would you open these doors? I'm still seeing a hand up from Lucia, so I'm just going to ask you.
Sorry, there was still up from the question with the lamp.
Okay, so now you have to say how you would open that door.
I would probably push.
Yes, you would probably push, and that's sort of the natural thing to assume. And that would actually work on the right-hand side. But the left-hand side, it wouldn't work, because the left-hand side, although it looks perfectly the same, is actually for pulling. Now, why were you thinking you push? Because the design of this big flat area here really suggests you want to push, right? It really doesn't look like something you want to put your hand around and pull on. So that's why this assumption, is the natural one. And if both doors were for pushing, we would have perceived affordances that were the right ones and everything would be good. Unfortunately, the left-hand side doesn't work that way. So that's why the people who were operating the store had to actually add labels. They added a label on the left-hand side because the flat surface on left suggests pushing. So you have to add a signifier, or a label in this case, that says pull. That's not great design, because we know from the right-hand side that we could have just used a naturally working, perceived affordance instead to be its own signifier. And because that now completely confused people, that the doors look the same, but one is for pulling, one is for pushing, they also added a sign on the other side and said, oh, this one is actually for pushing in the way that you probably initially suspected anyway. All right, so how to fix that in order to get perceived affordance to work would be to actually use different handles on the left and right side, that one suggests pushing and the other one really suggests pulling. Any objects that have a design award, by the way, are suspicious in this sense. There are many objects that you buy, like the hairdryer, probably won a design award, and I would consider design awards as warning labels. Right, so a design award is usually a usability warning label that will tell you, oh, I would double check whether this thing is actually usable or whether it just looks really nifty and cool, but isn't actually usable. Here's an example from IKEA. How would you open this this cupboard? This is for, I think, for shoes or something. I don't know exactly. What would you do? Elena, you want to try?
Because there's a handle, I would try to pull.
Yes, of course, you would pull the handle. And guess what happens? When you pull the handle, this is what happens. So it almost worked, right? So this thing was suggesting to you that you pull this thing downward. That's actually not what it supports, right? So it's suggested as a sort of as an affordance to pull downward, and I would call that a false affordance because it's not the way that you use it, right? When you do that, depending on how hard you pull, at some point maybe the door will actually open against the magnetic latch, but it would have made way more sense to put that handle vertical and toward the left-hand side, right? Because then it would have been perfectly clear if that handle had been right here, how to pull that thing open. So to summarize, we've got sometimes affordances that are false. So we perceive them, but they actually suggest something that's not possible. We can also have affordances that are unintended or accidental. And some examples would be, people sitting on a staircase, in which case you could say a stair is mainly for walking down, but it also is a sitting area, kind of like a chair. So it affords sitting, even though the designer did not intend that maybe. But if it's a nice area to sit, then that's actually helpful. Check out how people sit on the stairs leading up to the Rathaus, the town hall in the city center in Aachen. Another example here, that's from Norman's book, is this railing that you see here at the top of the stairs is so that people don't fall down, so it keeps people from falling off. But it also has a flat top that signifies or that has a natural tendency, an affordance, a perceived affordance for putting stuff down on there. So people started leaving their empty, drink bottles on there, which is in this case not helpful, right? That's an accidental affordance that the designer didn't intend, and that isn't actually helping in a positive way of using this thing. Now the cupboard you could interpret as, maybe it's a false affordance because the thing doesn't open the way they expect it to. You could also say it's a misleading signifier because pulling does work, but it's placed in the wrong place and that leads to suboptimal operation. We're talking about humans, we're talking about models of human thought, so there's always going to be room for arguing one way or the other. But I hope you get the general idea. Certainly, if you see the example at the bottom there with these doors that you pull, that is clearly because the pushing things clearly suggest something of push. The big flat surfaces suggest pushing, which is the perceived affordance, but it's not the right one. So I need to put a label on it so that I actually pull it instead. And finally, if you have a signifier that doesn't suggest the right action, then it's misleading, right? Just as an affordance can be false and not, trying to make you do something that actually physically doesn't work. A signifier that suggests not the right action is a misleading signifier. So the handle on that right cupboard can also be seen as it doesn't suggest the right action. It's signifying that I should pull here, but it misleads me because that's actually not the right way to open this door. Now, conceptual models. Apart from affordances and signifiers and this visibility issue, conceptual models are one of the most important things to understand about human-computer interaction. We have to understand that we are surrounded by countless objects every day. An estimate says that you have about 20,000 things that you somehow interact with, perceive every day. That's a lot of stuff. How do we deal with all of this? We haven't sat down and learned for every single thing how it works exactly in a lesson, right? We deal with it because we build conceptual models. That's how we cope. So our mind is wired to make sense of stuff. We've already seen that at work in our examples of the Gestalt laws and these kinds of things and visibility. Affordances of objects help us use objects easily if they are perceivable. And in general, if a designer designs a system that is very complex behind the scenes, he can at least try to create a good image of the system, what I perceive about the system. And that can be a good image of how the object works. And that is actually what we mostly do in software user interface design. We mostly create images of how the thing works because it actually has some, software running underneath the surface that does things quite differently from what the user is being shown. Whenever you encounter a new object, I used my scissors earlier as an example. Whenever we encounter a new object, we make sense of it. You can't not do that. It's hardwired into your brain to do that. Whenever you encounter a new object like these scissors, you immediately make a conceptual model of it. You immediately think, oh, 2 fingers here, 1 finger here. That's probably how it's being used. I had for a long time, I had wonderful pens that looked like you had to twist them to open them, but in fact, you actually they were designed to be pushed instead. Right? That's an example of you try to form a conceptual model because of what you see, and then if it's the wrong one, then you need to consciously learn things. But hopefully, for most cases, you don't have to do that. So providing good conceptual models is a fundamental principle of good design, right? It allows users to predict what their actions are going to do and to cope with any problems they might encounter. As an example, did anybody ever have to, get the internet working for their parents? Yeah, okay, so some people know. All right, so take any sufficiently advanced technology that your parents are not really excited about, but they know it kind of has to be there. So you're probably the person who needs to fix it. And so let's take the example of internet. You explain how the internet works to your parents, right? So you might say, okay, you click here, down there, click this little blue thing, and then click up here, and that will open this bookmark, and that's how you get to your page of whatever. And if you explain it in this like cookbook recipe, then your parents are going to build a model of how this thing works that's based on this cookbook recipe. If anything goes wrong, then they fail, right? If there's a system update and now the icon is no longer blue but yellow, they'll be lost, right? They don't know how to do this anymore. But if they've built a more complex conceptual model of how, for example, opening a browser works, if they understand what the concept of a browser is, what the concept of a web page is, what the concept of a link is, and stuff like this, then you can actually get them to have a more resilient knowledge and understanding of the environment and cope with problems, right? So good conceptual models let users predict what their actions are going to do and cope with any issues. We have mental models of everything. We've got mental models of ourselves, of other people, of the environment. Conceptual models are just mental models of things, of stuff, right? We form them either from experience because we've encountered something and played with it and used it, or because we've read some training or received some instruction on how to do that. And now comes an important graphic that I want to share with you that explains the difference between what the designer does, what the user does, what their understanding of the system is, and how these two relate. And this picture is quite important to understand, so pay attention with this one. Let's start with your job as a designer is to create what's called a system image, and that's sort of the user interface of a system. Now, the system itself could be, let's say, a complex online banking app. But you're not going to show all the complexity of how that online banking app works behind the scenes. You're just going to create a user interface to do certain things with that online banking app, like, for example, transferring money or checking your account balance. So your system image will have the user interface of your online banking app, and the system itself is the whole implemented online banking app behind it. Now, in your head, as a designer, you have a conceptual model that we call the design model of how online banking works. For example, for you, online banking means that there is such a thing as an account. and that there is such a thing as a transfer, right? A money transfer, and that there's such a thing as a balance, and those kinds of things. These form your mental model of online banking. Now, you build your system image, and so you built your system, and with it the user interface, the system image, that is the UI of your online banking app. And by building that system and its user interface, you will be encoding your model of how online banking works into the system image. In other words, the online banking app UI that you develop will feature things like accounts and balance checking and transfers prominently in the UI, because those are the concepts that you have in your head of how you think online banking works and how it should work, how you think about it. Now, in a lucky world, your mental model of how online banking works is the same as your user's mental model of how online banking works. But how do users arrive at that model? Well, users are going to interact with your system image. They're going to interact with your online banking app. And now two things can happen. In a perfect world, your user interacts with the system image, and by interacting with the system image, he learns the right model for online banking, the exact model that you wanted to intend and that you wanted to relate to them. And so in this case, the system image is a perfect transfer vessel for getting your model of how online banking is supposed to work to the user. And they get it, and it resonates with them, they understand it, they have the same mental model in the end of how online banking works that you had, and it wasn't a big learning effort for them because the system image made that very easy. But if your system image somehow isn't perfect, if this illusion that you create breaks in some points, then the user won't be able to form a consistent mental model of what, how the application works and how to use that interface. So when your conceptual model that you had in your head, the design model, is actually different from the conceptual model that the user forms of the system, then you have a problem. Let me give you an example here of that. There was a really old version of Windows called Windows XP. It had a trash can on the desktop, just like everybody else had at the time. And if you took a document and pulled it into the trash can, you could take it back out later if you changed your mind. That was the idea of the trash can, right? It was a way to delete files, but not really delete them, just throw them in the bin. And I'm going to delete them maybe at some point really from a hard drive, but for now it's just out of the way and it's flagged for ultimately being deleted. I'm signaling that I'm no longer interested in this file anymore, but I can retrieve it if I change my mind. This is great. People got that. People use the Windows trash can in exactly that way. But when you dragged a folder into the trash can on Windows XP, what would happen is that the entire folder's contents would get emptied and get thrown into the trash can, like you took literally a folder and emptied its entire content out onto your desk. So all the files in the folder hierarchy were being taken out of the folder and were all thrown into the trash can at a flat hierarchy, because the folder back in Windows XP didn't have, the trash can didn't have a folder hierarchy inside. What that meant is that once you dragged a folder into your trash can and then later tried to take it back out, you were screwed, because it had been completely disassembled and everything had been distributed all over your trash can. So if you had made a careful arrangement of years of data in little annual folders and stored things away, you pulled that folder into the trash can and you changed your mind, your whole lineup of all the data is actually gone, right? This means that the illusion that you were creating, the system image of a working trash can, was broken. It wasn't perfect. And that meant that the users now had to build a mental model around that broken system image. What people ended up doing, of course, is they created a folder on their desktop right next to the trash can that was called something like stuff that I want to delete, but I'm afraid to put it into the trash can because the trash can is somehow broken and eats my folders, right? So they would create their own sort of, secondary trash can, basically, because they knew that if they created that folder on the desktop and put stuff there, then their directory hierarchies would stay preserved. And that's a problem, right? This is not how we want user mental models to work. So this is an important concept to remember when you're designing user interfaces. You are creating a system image that the user interacts with that has usually nothing to do with how the system works behind the back. It doesn't have to be, but it has to be a consistent image of how the system should be thought of in the user's head, how the user should think about. We all know that there are no tiny little yellow folders inside our hard drives, but we still create that illusion to the user. And if you create this kind of illusion, then it should be consistent. So what that means is interface design, as an Apple UI designer put it many, many years ago, is he said interface design is all about crafting the user illusion, right? So we're magicians, which is awesome, right? Because who doesn't want to be a magician, right? But be aware of, the responsibility that you have as a magician, that your illusions need to be consistent. They cannot break down in a single part. Otherwise, users will have to build new conceptual models to work around those broken things. Or you may have a mental model that you think is perfectly clear. You put that in the system image, but the users have no way of understanding it because they think about the problem totally differently. And in order to resolve that, guess what? You will have to talk to users. You will have to understand how users think about your domain. If you write an app for, I don't know, gardening, you need to talk to gardeners and find out how they think about the domain, unless you happen to be a great gardener yourself and you know this stuff already. And we'll talk about how to talk to users and extract that knowledge in later parts of this class. For today, I just want to conclude by explaining the reading assignments to you one more time. The Norman book, you should have already ordered. You should have received it from Amazon or from your friendly local bookstore. For this week, you should get to until page 36 in the book, right? Start from the beginning, read it from the cover on, and get to page 36. You will have 4 weeks total to finish the book, and we will go through the topics of the book in class, but you do need to read this book, so you need to get it. If you don't have it yet, it's really, really time to order it quickly and get it tonight. We are already 12% in the book for you statistics fans out there, and we'll be moving fast, right? So this is not a book that we'll be reading over the course of the semester. It's a book that we'll be reading over the course of the next few weeks. Norman is required reading for this class. We also have these recommended readings here, the Dix book that I already mentioned. You earlier on had a recommended reading on that for the human, and here's a recommended reading on the interaction. These are 2 chapters from the Alan Dix book that are really useful to get a slightly different view on these things and get a better understanding of HCI. Also, Schneiderman has a wonderful chapter 2.4 on theories that will help you to understand some of the things we've talked about here even better. Okay, the Norman book you need to buy, obviously. The reading assignments you can find on L2P, the other recommended reading assignments. With that, I'm all done. We're at the 12:30 mark. Unless, Ollie, Marcel, are there any things that we need to still bring up?
Some students were asking for the version of the book. There is the 2nd edition, revised, expanded edition in yellow and one in gray. Do you know about this version, Jan?
The one that you should be looking at should be published in 2013, and I only know of this variant of it. So just make sure that you don't get anything before 2013. If this got reissued with a different cover later on, I haven't seen that, but that would be fine too. I would recommend going on Amazon or go to your bookstore locally, support your local shops if you can, and to get this book.
Yeah, there are only a few months between the publishing dates. I think one of the students wrote down that it's just another publisher, but I'm not sure. Again, we would recommend to use the yellow version. This is the one we consider. I don't think that it is a horrible thing if you have the other one, but
yeah,
if you have the choice, take the yellow one.
For sure. And if somebody already got the gray one and then discovers any differences by talking to other folks here, then we'd love to hear about it. We haven't seen that other one yet. All right, all set. Thanks everybody for joining, and have fun with the Norman book, and we'll see you next time.
This content was provided by RWTH Aachen University.